Hello, and we are back to continue with the quite extensive topic. This is the final topic we will cover in this class, and it's in the new Google Drive, okay, that I share to you, okay, in the Google Classroom of this class, and the name of the drive is called FFT Big Data Matlab, okay, over here. And once you found the link, that is a share link, you can find all the information that needed, okay. And it's gonna contain both the slide and Excel compatible file and also Matlab compatible file. So before we start the topic, I would like you to install, okay, if you have a Gmail, okay, address, okay, you can directly install the Matlab software, okay. Please do that, okay, by using the ku.th, the Gmail account, okay, and so that you can run the program. And the second program, the first platform that we will use is we call the Excel, okay, the Excel format, okay. And the topic that we gonna cover here, okay, first we call Discrete Fourier Transform. Okay. You might familiar with the term we call the Fourier Series, okay, which is summation to infinities, okay, for set of sinusoidal with the range of frequency, okay, for the sinusoidal signal, okay, and that we call the Fourier series, okay. And but this one we're gonna study different definition. We call actually we call Fourier Transform first, okay. But once you try to discretize it, it becomes what we call the Discrete Fourier Transform. And we're going to start talking about computational point of view, okay. And it certainly this problem become well known and has been using in many applications. Okay. And but since this is a mathematics course, we're going to start talking about it in mathematics point of view first, okay. So let's start with the definition of what we call what is Fourier transform. Okay, the first equation that you find on your screen here, this line, okay, we call the capital X in terms of omega is equal to integral from 0 to capital T of the function e to the minus I is square root minus 1, okay. I times omega times t, okay, this is the power, exponential power, time for a specific function we call f of t dt, when t running from the range of domain t running from 0 to t. But you can see that once you find this integral, okay, the domain t vanish, okay, with this evaluation. The remaining parameter, okay, the domain in the function is only this omega value. That's why this capital X become the omega, the function that rely on omegas, okay. And this is what we call the Fourier transform. If you might recall, you might remember the e to the exponential of minus I times theta. You might remember, right? It's become what we call a complex conjugate of the complex number of what we call the cos of theta minus I times sine of theta. So in this form of the exponential of minus I omega t, okay, if you expand it, it becomes a complex number referred as cos omega t minus I times sine omega t altogether, okay, times f of t, which is a real value, okay, continuous real value along the interval from 0 to capital T, okay. Why we are doing this, okay? Fourier Transform was set up, okay, historically, okay, in parallel with what we used to have found in as a general solution for partial differential equation. As you see when you study partial differential equation, you might recall that the general solution is in the form of Fourier series. But Fourier series is not the integral form. It's in the summation form. And you have to know that once it's in the summation form, you have to know that f of t, okay, if you apply for Fourier series, it becomes a periodic signal from 0 to t. Okay, it means that it's become a continuous signal go forever, okay, but have a repeated pattern from every capital T period. Okay, but for Fourier transform, we only consider within the interval of 0 to t. Okay, outside the interval, okay, less than 0 or more than t, we expect that f of t is 0. Okay, so that's why this form is a little bit different than Fourier series. Okay, let me remind you again, when you study Fourier series, f of t, okay, need to have what we call the periodic assumption or cycle, become a cyclic signal, okay, which is repeated itself every period of capital T. But for Fourier transform, okay, we only consider the effect of f of t over the period 0 to t, capital T. Okay, and again, you can see that the reason they multiply by exponential of minus I times omega t is because the real term, okay, the real part of this number, okay, will be cos omega t times f of t, and you find the integral from 0 to t, and the imaginary part is becomes minus sine omega t times f of t. Okay, actually this minus sign can be either plus or minus. It doesn't even matter in mathematical point of view. But in application point of view, there's some motivation to using the minus sign. Okay, and with this notation, I'm going to tell you a little bit about the reason because what is it useful or the benefit that you using this Fourier transform? Okay, you can see that the Fourier transform is a function that transform any specific function that rely on one domain. This one we call t, the small t. The reason they use a small t is because they expect that to be a function that change over time. Okay, for example, if you consider any specific value that change over time, over a period, over a specific period, finite horizon of capital T, okay, you can change this signal, okay, within this interval, okay, to another domain, okay, we call the omega domain, okay, by multiply using this transformation. And what is it benefit that you try to do this? Okay, let's consider the notation omega. Okay, way back, if you might recall or you might remember, okay, the omega is a notation of what we call the angular velocity, okay, which is omega is equal to 2 times pi times frequency. Okay, so in this transformation, okay, you might say that the x function of Fourier transform is changing the effect of the specific data that change over the time domain. Okay, and consider its influence within the frequency domain. Okay, that's and why is it this important? Okay, because once you be able to identify the influence on frequency domain, you might know that, okay, that's why that's the happening of why you have a frequency modulation for the the radio signal in the past, okay, and also the way that you can eliminate what you call the interference, okay, within several different type of the bandwidth of signal. Okay, so it become a big deal for especially for communication engineering. Okay, and also they say also play a big part of many applications, even in the stock market. For example, if FFT is the amount of you buying or selling within the period of T. Okay, if you use this formula, okay, to change to the omega domain, okay, which is the frequency domain, you're able to identify, the what we call the bandwidth of buying and selling. Okay, you know that within the frequency domain, you will know that what is the most frequent bandwidth, okay, that people selling or buying. If you watch the signal within the time domain, you're not going to be able to detect it. But once you change it to frequency domain, but you might be wondering if the frequency domain, you can, as I told you before, that it's in this form, it's going to be a complex number. How am I going to, what is this complex number going to look to me that has some meaning to me? Okay, you remember that if you have a complex number, you can change it by considering the magnitude. Okay, the magnitude is the real part, the square root of the real part, okay, square of the real part plus the square of the imaginary part. Okay, the magnitudes mean that the strength of the influence, okay, within that omega, within that frequency. Okay, and also you can study what we call the phase angle. You find the arctan between the real part and the imaginary part. Okay, it's gonna tell you that what we call that the lead and lagging of, if it's a minus sign, that the reason they use a minus sign is because of this. That most likely that what you saw, what you see now, or the signal that you see now, is have some what we call when you see it, it already behind what's happening a few minutes or a few seconds ago. How do you know that the times lag, the lag time, that the real signal, okay, that happened? Okay, this one you apply for when you look at the signal in the radar. For example, if you want to detect something flying or in the sky, or something, some swimming under the water, okay, and the reason once your instrument detect that data and transport that signal for you to see on the screen, okay, but that object is still keep moving. So the location that you saw on your screen and the real location that they move, there are some what we call the lagged signal, okay, which means that the location that you saw on your screen is not the real location that you saw, that they are moving now, because once you get that location on your screen, that object already moved on. Okay, and that's the way that if you want to know more about this, you have to go to study communication engineering or signal processing, okay, and the time series analysis that have a major application in many aspects. Okay, but in this course we mainly concerned with the mathematics computation of this function, and that this function can be derived exactly if you really know what is f of t. Okay, if f of t is a well-defined function, for example, it becomes sinusoidal function, the sine, the cos, the tan, or whatever, the polynomial, okay, the ratio of the polynomial function, whatever. If it's integrable, okay, let's just say that if the function is integrable when multiplied to this exponent function, okay, so you can derive the exact formula for capital X in terms of omega. But in reality, when you apply it to the real signal of the world, which normally consists of what you call the pattern that you are looking for. But the reason that when you can't detect those patterns is because that there's always the interference, the noise that gonna make your signal a little bit shaky and also not in the well-defined pattern. So in practical, when you get the FFT, it's very hard to find the right function that represent the FFT here. And this is cause the problem of computing this function, because your integral here cannot be integrate this function because this function cannot be defined. But you know that you can have a sensing all the signal within the resolution of your instrument, and get the results of several discretization of FFT over the range of 0 to capital T. And once you get that situation, which means that your FFT is not integrable, you have to go back to the basic of how you evaluate the integral when FFT is not well-defined function. You're going back to use well-known what we call the integral is the area under the curve. So you can discretize the FFT to a very small value. In this case, we're gonna apply here. We let x of 0 is f of 0, x of 1 is f of delta, and x of 2 is f of 2 times delta, up to capital N minus 1, we call f of n minus 1 delta. And we expect that when you and once t is equal to capital T, f of t become vanish. So it means that x at capital N is equal to 0, which means that n times delta, because n times delta is capital T. So one is we discretize the T domain with the resolution of delta. Resolution is meant that the most accurate, because T is a continuous. If you say that how many points of T between 0 to capital T in classical mathematics as a continuous random variable T, from 0 to T, you expect that there exists infinite number of possible value of capital T. But in reality, you'll be able to detect this f of t, over time with some instrument. But all instruments, just like you study the stopwatch or even the clock that you use on your mobile phone, they're going to have some accuracy, the resolution, how precise your measurement going to be. Is it a 3-digit or 4-digit of number, and delta is defined. For example, if your result is accurate within first 3 digits, so your delta have to be 0.0001, or 0.0009, so that the fourth digit start to become some error too. But so delta define precision or resolution, and if you discretize this f of t, to several point, in this case we approximate to n point from 0, 1, x of 0, x of 1, x of 2, up to x of n minus 1. That's the only thing that you know about f of t. You don't know the exact f of t function. Therefore, it's not integrable, but you know the definition of integral is the area under the curve. So if you change this integral to summation, it becomes the area. So this term need to multiply by e, this, and then dt become delta here, the resolution here. So beyond this, if we identify that if x bar sub k, is equal to n equal to 0 to n minus 1, and we define new term we call w to the n times k. What is w going to be? W in our case is e to the minus I times 2 pi divided by n. This is w. Therefore, w to the exponent with the n times k become e minus I times 2 pi divided by n times small n divided by capital N times small n times k. What does this mean? Actually, this is the term here. But you might wonder, how it's going to be like this? Okay, certainly minus I, you know, but your omega, you know that is by definition of omega is a 2 pi time frequency. Okay, 2 pi time frequency. Okay, but what is the frequency here mean? It's a domain frequency here. Once you discretize the domain T, okay, by resolution delta, your domain F, okay, or frequency or omega here have to be discretized with resolution delta also, which means that for each, okay, n here equal to 0 to n minus 1, which is a discretization approximation at this integral here, okay, become x sub n here, okay. But actually, though, this whole term, x omega here, okay, can be approximated with x bar times k times dt here, the time delta, okay. But since delta is all the same, okay, so they're gonna multiply it later at the end. But to be able to approximate this integral, we approximate this integral by summation, okay, from 0 to n is what? N, so 0 to n minus 1. Because you know that at that time t equal to small t equal to capital T, f of capital T is equal to 0 according to this definition. So the summation have to start from only n equal to 0 to n minus 1. For each of them, f of t is along this, okay, with this definition. Okay, but they need to, for each term of this summation, need to multiply by e exponent to minus I omega t. Minus I is here, but omega is 2 pi times f, okay. But as you know that for each omega k, okay, for each omega k here, okay, we also look at here that the definition of omega is 2 pi times frequency. But the frequency is, definition of frequency is that is the 1 over period that you are interested. And in this case, your period is t. But you must remember that your t here have been discretized to 0, delta, 2, delta, delta. So this is all possible frequency resolution that you can consider. Okay? When k is 0, okay, so it means that no more frequency. It's a frequency, 0 frequency situation. But for k is equal to 1, is considering at at t is equal to n times delta. Okay, when k is equal to 2, is a half of the period t here. Okay, it become t divided by 2 and t divided by 3, 4, 5 up to n minus 1. You might wonder, what about n? If 1 over delta, is that possible? 1 over delta? Okay, if k is equal to n, so that n the resolution of the 1 over t become 1 over delta. In this case, we cannot do that, because you know why? Because you know that because the resolution of delta n at time t, okay, the signal has been vanished. Okay, so once the signal has been vanished, you can't expect that k can be equal to n here. Okay, so let's summarize this. Once you discretize the domain t, okay, to 0, delta, 2 times delta, up to n times delta. But you know that at n times delta, you don't have x sub n capital N. You know x sub capital N is equal to 0. Okay, but this one is all possible non-zero. Okay, and therefore, once you discretize this t, you discretize this omega by k parameter also. Okay, and substitute it with 2 pi times k divided by t. Okay, and when k is equal to 0, so it means that it's, let's just say that it's a non-frequency signal, no effect signal based on frequency. But k is equal to 1, we consider the whole length of the signal t, just half, 1/3, and so on. But you can't expect to have t over n, because you know why? Because at the end ft is equal to 0 and t is equal to t. So ft is effective while only until t is equal to n minus 1. Therefore k can be discretized up to only n minus 1. And you know that x omega k, okay, with this to approximate the classical Fourier transform, you need to multiply delta at the end once you evaluate this x bar k. But that's not the big deal. But the big deal now is how to compute this x bar sub k. Okay, and this w here, okay, why it become like this? Because you find the summation here for n, okay, t moving along with n, okay, but this n here, okay, you know that this omega here, okay, is equal to, since you apply omega here, is 2 pi k n divided by capital N times delta, okay. So once you find x bar w to the k here, okay, w to the k time nk here, okay. So you can see that when this omega e here, okay, and then you time n small n and time k, okay, w to the nk, okay. You can see that those delta here, okay, just cancel to each other, okay, because t start from 0, delta 2, delta 3, delta. So when you, for any n, okay, t become n small n time delta, and small n time delta divided by time omega k divided by a capital N delta. Therefore delta cancel, okay, from the ratio. That's why the remaining w is like this. That's why w this term can be used as w to the n times k, okay, to the n times k, because you can see that t become only n delta since delta cancel, okay, n here, okay, and omega, okay, that's only thing left is k, okay, k, and divided by this one divided by n, okay. So in the next part, okay, we talk more about the computational issue of this discretization, okay. So let's summarize again, okay. The first equation is a definition of what we call the Fourier transform, okay. The difference of Fourier transform to Fourier series is that Fourier series, you need to consider what we call the periodic signal of FFT. But for Fourier transform, we only consider what we call the transient signal within the interval of 0 to capital T, okay. And Fourier series is in the summation form. But Fourier transform, okay, you consider in a continuous form, okay, and you find all the effect of t, okay, within that interval, okay, by multiplying this exponent of minus I times omega t to f of t. Okay. And since f of t cannot be defined analytically, okay, or mean that as a well-defined function, you only get what we call the discretized function. Therefore, to find the x omega here, you need to find x bar k here. X bar sub k here require this evaluation, computation of this summation. And you can see that to evaluate x bar for each k, okay, in here, over here, I think that we might make a mistake here. Actually, this small k have to start from 0 also, okay. K is not starting from 1, okay. K has to start from 0, 1, 2 up to n minus 1, okay. K is equal to 0, 1, 2, 3 up to n minus 1, okay. And you can see that for each k, okay, it requires summation of a multiplication form of n term, since a small n, capital N term, since small n is equal to 0 to n minus 1. So for each k, okay, you require capital N multiplication and capital N summation, okay, for each k. And you can see that how many k? Since k start from 0, 1 to n, you also k have the capital N possible. So to evaluate all this x omega k for all k, and you will require to have, in terms of dependent function, we call the capital N square. Okay, capital N square of multiplication and summation. Okay, why n square? Because each k require capital N, okay, of summation of this product. Multiplication of this product term, and then for each product term we need to sum it up for capital N time. So for each k you require capital N multiplication and capital N summation. Okay, but k have capital N possibility. So to finish evaluated x bar omega k, okay, you would need, okay, to get this x bar k, okay, you need n square multiplication, capital N square, and capital N summation, capital N square summation. Okay, and you might say that with the today's computer development, what's wrong with that? We can do it this easily. Yes, true. But you know that with the advancement of instrument nowadays also, the resolution of data become highly precise. For example, it can go down to 6-7 digit accuracy. With delta is approaching 0. Okay, to make this integral well established approximation, you need delta, as you know from calculus theory. Delta here, okay, need to be approaching 0. And today delta keep getting smaller and smaller. When delta keep getting smaller, the capital N become larger, because you can't, there's a finite horizon of capital T. So n times delta equal to t. Once delta is so smaller, capital N must be bigger for a specific t. Okay, and when capital N become larger, to complete evaluate this approximation of x omega k for k require much more. For example, if your delta is like 20 digit accurate, okay, we mean 0.00020, 0, okay, so you end up, you know that for t is equal to 1, you know that n times delta is equal to 1. So you know that if delta is a 20 digit accurate, capital N have to be 10 to the 20. Okay, 10 to the 20. And you, to finish this, you need capital N square. You become 10 to the 40 multiplication and 10 to the 40 summation. And at one point, your computer gonna stop. Okay, you can't expect to keep adding up and make your hardware as efficient. Okay, so the longer stream of this approximation, the computing of discrete Fourier transform become slower, okay, because it's the number of multiplication and summation increase as a quadratic function. Okay, and that's the start of all the problem that this is a situation here, that how can we reduce, okay, this computation issue. Okay, and in 1965, okay, with the classical work of what we call the Coulomb-Tukey, okay, and I also, okay, if you go back to this link drive, okay, you double click here for the folder, subfolder we call the related document for Fourier Transform big data here. Okay, actually many documents here can be studied within one semester. Okay, 45 hours, but in this case I just give you all the information, but we're not gonna go through all of this. Okay, but we have to go to this paper. Okay, so this is a very important paper. Remember Coulomb-Tukey, Okay, over here, Cooley-Tukey, 1965. This is also 1965 April. It was published in the journal we call Mathematics of Computation. It's a very, very well-known and very famous journal, okay, published by American Mathematical Society. Even today, this journal still exists, okay, and this is one of the landmark papers. But look at the name of the paper. They say the algorithm for the machine calculation of complex Fourier series. Okay. They talk about Fourier series. They didn't talk about Fourier transform. But how come I say this as Fourier transform instead of this talking about complex Fourier series? Okay. In the before we finish the lecture, which will be a couple of clips next, okay, I will demonstrate to you the relationship between the computing of the Fourier transform here, okay, and the relationship with we're gonna go to advanced here, okay, the Fourier series here. I think that you're familiar with this formula of Fourier series from our previous lecture of the general solution for the partial differential equation in both that wave equation, that heat equation, and that Laplace equation. Okay, so this is a well-known Fourier series, but this is a Fourier transform. Okay, but to compute this Fourier transform, okay, actually you need to use this algorithm presented by this paper. But in this paper, they say nothing about Fourier transform. They say about machine calculation of complex Fourier series. Okay. And it's a very short paper from Cooley and Tukey. It was written about 5 or 6 pages only. Okay, and only have 2 references. You might really, well, only 2 references. Okay, the first one is paper by Box, Carter, Cousin, and Davies. It was actually these 2 papers related to the experimental design of statistical method for experimental design. Okay, and but this is play a major role what we call, okay, first of all they talk about 2 to the n factorial experiment, Yates. So if you study statistical experimental design, you're familiar with this thing. But very few people know that this is where it all starts, from Cooley and Tukey. Okay, but this algorithm, okay, that Cooley-Tukey wrote for 5 pages here, become known, okay, and can be summarized by this part that I show you on the screen. We call this a radic tool. Okay, radic is mean that the related to the number that has a base set of 2. Okay, for in other words, it's 2 to the n. Okay, 2 to the k for any positive k. Okay, and you might remember that this is the evaluation we are looking for from the first slide here. Okay, this x bar k is this evaluation, but let me write you k 0 is also exists. Okay, k start from 0, 1, 2, 3 to n minus 1. Okay, and you can see that we change here, right? K is equal to 0, 1, 2, 3 to n minus 1. This is the x bar k according to this approximation of what we call discrete Fourier transform. Okay, and let's look at the idea of what we call classical laddic tool. Yeah, that based on this presentation of Cooley-Tukey way back in 1965, they're using you can say the W here is the same W that we use here, the same W here that follow the spirit here. And but a little bit this one you use A at K, okay, instead of use X sub n, just like what we are doing here. So we're gonna explain this concept by using this notation, okay, that we are using here. Okay, let's start with this term. This term is coming from the discretization of this integral form of Fourier transform. We call this discretization, discrete Fourier transform. Okay, and to compute for each omega k, okay, you need to find x bar k, and x bar k can be written in this form. Okay, and you can see that x bar k here, we're going to split this summation to two terms. Okay, so the first term we only consider at x with their index according to the even number, which is n is equal to 0, 2, 4, 6, 8, 9, or 2 times n. Okay, and the remaining odd term, okay, in the odd order term, okay, we're going to represent to x to the 2 times n plus 1, since n start from 0. And you can know that now you can separate this summation into two terms. The first term is only consider the order term in the even for the even term, this one. So n have reduced it half by half here. N is equal to 0 to n by 2 minus 1. Okay, this is half term of this. Okay, and since x, okay, we only consider the even order. So xn become x times x sub 2 times n. Okay, for every even order, x0, x2, x4, x sub 6, x sub 8, and so on. And w need to change for n to 2 times n also for this exponent. Okay, so this one change to here become this. Okay, and for the odd order, okay, for the odd order become, you just replace n by 2 times n plus 1. So the xn will become x sub 2 times n plus 1. W to the n times k become w times 2n plus 1 times k. 2 times n plus 1 altogether times k, you get 2 times nk, okay, and plus 1k here, you can, since w to the k, okay, not relying for any small n, so you can, it's become a common multiplication term. You can move it out here, w to the k. Okay, and then you get this special properties here. Okay, if you replace a k by k plus n divided by 2, okay, you get this value. Okay, which means that if I replace k by k plus n divided by 2 here, this time, okay, this term, okay, if you replace k by k plus n divided by 2, become w to the 2n times k plus n divided by 2. Okay, okay, and x to n is the same because it's not rely on n. And with this complex number property exponent here, you can show that w to the 2n k times k plus n divided by 2 is equal to w to the 2nk. Why? Okay, let's look at briefly here. Okay, so if you replace k by k, the first term k, okay, you get this. But the second term n divided by 2, if you use 2 times nk times n divided by 2, okay, 2 cancel each other out, it becomes w with exponent of small n times capital N. And w with exponent of times n times capital N, okay, it become what? Because you know that w is e to the minus I 2 pi divided by n. If you find the exponent of w by small n times big N, okay, the big N will cancel each other. You get only e to the minus I times 2 pi times small n. And it become, you know, with this expand as a complex number, it become cos of 2 pi times n minus I times sine of 2 pi times n. And you know sine of 2 pi times n is always 0 for any integer n. sine 0, sine 2 pi, sine 4 pi, sine of 6 pi is always 0. But cos of 2 pi times n for any integer n, including 0, is always equal to 1. Okay, be with me? Okay, w, okay, you need this w. Okay, when you replace k by k plus n divided by 2, the first term is you get this, but you need to multiply the second term is that w, okay, times, okay, times small n to no, not w with exponent of small n times capital N, and w with exponent of n small n times capital N, you get e to the minus I 2 times pi times small n. Okay, that resulting the complex number of cos of 2 pi times n minus I sine 2 pi times n. With for any value of integer n, you're gonna get is always equal to 1. When it's always equal to 1, that's why this term, when you replace k by k plus n divided by 2, you get the same term here. Vice versa, when you apply here wk here to this second term, when you apply to this within this summation of w to the 2nk, you get the same, even you k change to k plus n divided by 2. But once you apply, look at the common multiplication term here, w to the k. When you apply, substitute k by k plus n divided by 2, k plus n divided by 2, you certainly you get w to the k. But second term you get with this in the exponent you get w to the k times w to the n divided by 2. And when you apply w n divided by 2 here, n divided by 2, you get what? N cancel n, 2 by 2, you get e to the minus I pi. That you get cos of pi minus I sine of pi, which is equal to minus 1. Okay, you see w, okay, with exponent of capital N divided by 2. Okay, so this one with exponent of capital N divided by 2. Therefore, n and n cancel each other out. 2 and 2 cancel each other out. So you get the remaining term of e to the I times pi. And e with exponent minus I times pi is always equal to cos pi minus I sine pi, which sine pi is 0 and cos pi is equal to minus 1. That's why the second term you get this minus value. Okay, and this is the clear explanation of you separate this summation to 2 terms, and only here, okay, you can see that k is reducing by half here. You don't need to find for all k here anymore, because you can see that these 2 terms is the same. The summation of the remaining term is the same. The difference is that once the first term for the half of the previous k value, okay, when k is equal to 0, 1, 2, 3, up to n divided by 2 minus 1, okay. Once you separate these 2 terms, okay, the remaining n minus 2 term is, you don't need to evaluate all of them. You can use this summation, okay, and just minus the first term, just plus each other, the second term just minus each other. So approximately you can see that your work reduced by half. Remember that for the original summation here, for each k you need n multiplication, capital N multiplication and capital N summation. But once you split these 2 terms, okay, the first term, okay, the first k reducing by half. So you need to evaluate x bar k, only half term. But from n to n minus 2, only n minus 2 term. The remaining n minus 2 term, you don't need to find another, for each k, you don't need to find capital N multiplication and capital N sum. You only subtract, only use one subtraction. You see, you only use one subtraction here, because you already know that in the first initial half of n, of capital N, from here. Okay, so actually almost a half of work have been reduced by using this, what we call and you know the reason they use radic 2 is because we split this summation to two terms. Okay, and you get this property, and this property helps you to reduce the computation by half. Okay, and again with this, each of these summation here for this odd term, the odd order term, and this odd order term and even order term, you can also keep applying this radic to separate these two functions into two summation terms. Okay, that's going to help you reducing evaluate for each of these summation by half. Okay, and you keep doing that until this summation reducing down to just two terms. Right? The summation is only two terms. Okay, and with that summation of two terms, you're reaching what we call the original x value. Okay, and that's the whole idea, that it keep reducing half. Okay, and you can see that, for example, okay, if n is equal, capital N is equal to 8, okay, we separate by half here, okay, for each of these terms, okay, you get each term 4 terms, summation of 4 terms. Okay, and for this summation of 4 terms, you separate it another half, you get another summation of 2 terms. And those summation of 2 terms is just a direct multiply and subtraction of the original x value. Okay, so you can see that the computation has been reduced. Reduce it to what? You can see, for example, as n is equal to 8, okay, you separate these two, okay, you reduce it by half, but for each of these, okay, you separate another 2, you get this summation, and you get another two summation. For each of them consists of the 2 term, and that 2 term you reach the original x here. So the computation have been reducing from instead of you need to 8, for example, capital N is 8, you need 8 multiplication and 8 summation for each k, and k have 8 possible cases, so you need 64 summation and 64 multiplication. But using this radic 2 here, okay, you keep reducing it, okay, to, you can see that at least for some stages you have, the first stage is summation, and this separate this, you get 8 term, okay, and the second stage, okay, you reduce, first stage you reduce 8 to 4, second stage reduce 4 to 2, and the third stage is 4 to 1 to the original one. So the stage of computation reduced to only 3 stages, and for each stage, okay, you need to compute 8 values, okay, of this summation. So instead of you need to compute 64, you only compute 8 times 3, because your stage of computation reduced from 8 to 3. And 3 is, what is this 3 value coming from? It's coming from log base 10 of number 2 of the 8 value, which is 8 is the number of what you call, S is the number of discretized point. Okay, so that's why they call this fast Fourier transform. Fast is because instead of you computing 64, okay, you reduce from 64 multiplication and 64 summation, okay, to only, and dealing with complex number, okay, and to only 24. And 24 is coming from 8 times log of 2, or the base 2, base number 2 of the 8 value. If you have a very large n value, okay, the large n value here, just like what we discussed here, for example, for a very large n value here, okay, the complexity is reducing down to only n logs based number 2 of capital N. Okay. Think about N as a very large number. A number of times you reduce it become N divided by log 2 sub N. Okay. Which if for a very large N number, it's going to be tremendous decrement of the computation time. And that's come the whole idea of what we call the fast Fourier transform. Okay. And the whole idea that I just explained is once in 1965 it has been explained in this paper. Okay. But bear with me a little bit. You can see that this paper didn't say anything about Fourier transform, but just go back and say about Fourier series. But you might wonder that how come this talk about Fourier series but can be used in Fourier transform? Actually, this is a Fourier transform. Okay, but it's a discretization of Fourier series. And we can show you later with discretization of the Fourier transform. It becomes a part similar to what you're looking for to find the Fourier series coefficients. Okay, this one you can see W we're using the same formula, e to the this, but they use 2 pi I. Okay, they didn't use minus. Okay, but in our case, okay, we use minus. Just like what I told you, there can be plus or minus, doesn't matter. Okay, and you can see that the reason they have keep summation here, okay, is the same as if you trying to this one, you can also discretize using the same format. There's to separate this summation, half term summation here to another half, and so on. Okay, and that's the reason we explain here, and this one here they show here. Okay. When n is become, n times log of r. And this one, the small r, we call the 2. Okay, this one, okay, is a reduction, okay, of time reduction that you can see that r divided by log 2 of r. Okay, if r is a very large number, okay, it keep increasing. Okay, keep increasing. And in this case, the obvious way that you can define what is the n value here is that if we set up the capital N value as a 2 to the with the exponent of some integer value. For example, you can get the capital N as maybe 1024. 1024 is 2 with exponent of some positive value. Or maybe you add, once you know 10,024, you can go to 2048, 2048, okay, 2000. And then for once 2048, you can go up to 4096, okay. It's in the 2 to the 2 with the exponent of the integer value, okay. So that's a restriction of this, what we call the classical lattice 2, okay. But we're not gonna do this, okay. Let you do this by hand alone. First of all, okay, we want to demonstrate something for you, okay, and that is this by using this file, okay, the FFT big data, okay, and this file that you can find it over here, okay, is in this Google Drive, okay, here. Okay, you call FFT big data here. You can download it and open it and take a look at it. Okay. Luckily that within the Excel format here, they already install something that you can compute. Okay, we call the data analysis. Okay, options. Okay, within this data, and you can see that with data analysis here. Okay, there's a function we call Fourier analysis here. The Fourier analysis over here, okay, that you find within. If you don't have this on your screen, the data analysis, okay, you can install it, okay, by you go to the options, okay, and you go to the add-in function. Okay, you need to add this analysis 2 pack. okay, and you go to the Excel add-in, okay. You, in this case, I already install all, okay. You have I already click choose all of this, okay. So I don't need to. If you don't have it, you just click to get the choose sign, okay, and then all of this will install to you over here, data analysis. And once you call data analysis, you can see that there exists what we call the Fourier analysis here. Okay, and the Fourier analysis is a tool that can help you, okay, to compute, okay, this. Oh, sorry, we already installed it. Okay, to compute this, okay, x bar k here, okay, they can compute x bar k using this concept of radix 2 or Cooley-Tukey here, okay. So I'm going to end up this script here at this point first, okay. In the next script, we'll demonstrate you the limitation of using Excel to based on this data file, FFT big data, using the what you call the tools, okay, data analysis of Fourier analysis here. Okay, there's some limitation, and we're gonna come back with the definition of this Fourier transform with some extension, okay, and modification of this idea, okay, to help you to solve the problem with a very long stream of data. Okay, in this case, that's why we name the file as FFT big data. Okay, using the Excel format. Okay, and then we're going to expand this and try to apply it using what we call the Matlab format. Okay, and I already told you that you can use the Google Gmail code and install your Matlab on your computer, and there's some very good coding, okay, coding available for you that help you to compute the fast Fourier transform. Okay, so I'm going to end up here first. Okay, I'll see you in the next clip.